Welcome to a video on basic MOS differential amplifiers. In this video we will have a look at the DC analysis of one of these amplifiers, the differential and common mode input ranges, common mode and differential mode. We will look at the gains, output impedances, input impedances, etc. Then a little bit on the output offset voltages, and lastly we will look at some simulations of what we do in the analysis. Okay, so first off, here on the right hand side we have a nice MOSFET based differential amplifier, and the assumption is always that the MOSFETs and the resistors are matched. It's driven by a current source. This current source can also just be a resistor, but we will get to the negative effects of having a resistor here a bit later. But typically some form of current source which will sink current from both sides of a circuit and provide the bias. The differential amplifiers do not need external bias resistors like we had. They are self-biasing. That's one of the advantages of using differential amplifiers like this. So before we start the analysis, in a previous video we spoke about common mode and differential mode. So when we're doing common mode signals, we will be putting in it on both inputs, and when we're doing differential, it will either be the full signal on one half of a circuit or a non-inverted and the inverted version of a signal distributed between the two inputs. Okay, differential also means that we look at these two outputs and the load will be sitting here in between, and we subtract the one output from the other. So typically Vout2 minus Vout1. The DC will cancel and the signal will be sitting in the middle right here. If we talk about single-ended mode, it is just taking one output of the circuit and not the fully differential output. So throughout this presentation, the transconductance of a transistor that we will be using is 100 milliamperes per volt squared. The threshold voltage is 1.5 volts. The current source provides 1 milliampere. The lowest voltage across the current source is 1.6 volts. Typically, a current source like this is built out of transistors. So if you take the voltage drop over that transistor too low, it will stop providing the correct amount of current. And that is the VCS that we're going to use later is 1.6 volts. And drain resistors of 10k each. Current source usually has impedance of its own, so for this one we assume 100 kilo ohms. If we are using a bias resistor to provide the same 1 milliampere, we need a 8.2 kilo ohm resistor for these problems. So these are the resistor RSS values that we will be using in our problems. Right, so first, as I said earlier, we always assume that we have matched transistors in our circuit, matched drain resistors, and so on. Now, this current wants to deliver 1 milliampere to this circuit. So if we ground both the inputs and these circuits are matching, an equivalent amount of current will flow through both of them. And this is how we find our transistor's bias. So the current source value divided by 2 will be flowing in each side of this circuit. That is also the current that we're using to find our small signal parameters. Right, so basically the drain current, both of them are the same, which is half times the current source. We assume that we are working in saturation since we are building an amplifier or using an amplifier here. From that we can get our gate source voltage. So 1 milliampere divided by 2 is 500 microamps. VGS1 is equal to VGS2, and that gives us 1.6 volts right here. So 2 times ID from the equation, so basically the root of our 1 milliampere over the transconductance plus our threshold voltage here. Okay, so this part right here is our overdrive voltage. So the current that you choose gives you your overdrive voltage, and that has influence on our differential input mode. So this has a significant influence on the signal sizes that you can provide to this circuit. Okay, then our two drain voltages will be the same. So VDD minus I over 2RD. If this is 10 volts, then it will be sitting at 5 volts on both sides. So in terms of biasing, having this point in the middle between our drain resistor and our drain source voltage is achieved. So this is the Q point. So it also means if this is in the middle of our VDDs that we can provide full output swing for this amplifier. I'll show you that in the simulations. Right. Our common mode input range. This is when we provide very large signals into our amplifier, but the same input on both sides. So our current in both sides will remain the same if we drive these inputs to be the same, and they will be subtracted equivalently at these 2 points. So if the voltage on this side increases and this side increases, the difference across a load here will be 0. Okay, so to find our common mode input range is we need to see how far we can push these transistors until they are not in the saturation region anymore, or until we drive ourselves into one of the rails. Okay, so let's define Vs is our common mode minus our VGS values. Right? We also know that our drain source voltage should be larger or equal to our overdrive voltage. So our VDS can be split up into our drain voltage minus our source voltage, and our overdrive voltage is our gate source minus our threshold. We know that our drain voltage is VDD minus I over 2 times RD. We can plug that in right here. And our VS equation we can plug into this position. With that, we can find that VDD minus I over 2 RD minus our common mode plus VGS is equal to our overdrive voltage. So our VGS's will cancel from this, and if we get our common mode alone, we find that it's VDD minus the bias current over 2 times RD plus our threshold voltage. So our maximum common mode signal is 6.5 volts. For the minimum, we just take the loop down here. So our common mode is our VGS plus the drop over our current source. So we should consider the minimum amount over our current source and our bottom voltage rail right here. So our VGS is 1.6 volts. Our drop over our current source at the minimum is also 1.6. If this was a MOSFET kind of deal right here, you would go and see when it stops functioning correctly. And plus VSS is just minus 10 volts. So our bottom or our minimum common mode signal is minus 6.8 volts. Now if we want to see our input range, we can ground one half of our circuit and we insert a full signal on the other half, right? And we drive this transistor until there is no current flowing on the second half and we have a maximum amount of current flowing through this transistor and resistor right here. So current source equals to the current. Okay, now we try and find our gate source voltage again, and we will find that it is 2 times this current over our transconductance plus our threshold. But we know that our overdrive voltage is the root of I over Kn. So we will have a remainder of the root of 2 times our overdrive voltage plus our threshold voltage. So this is our gate source voltage when we are driving this transistor to its maximum. At that point, Vs right here will be sitting at the negative of our threshold voltage, and we will find that the input differential is VGS plus Vs. So if we just want our VGS right here, and that means our differential input voltage at a maximum is the root of 2 times our overdrive voltage. So if we need to increase our input range, we need to increase our overdrive voltage. Okay, for this problem, our overdrive voltage is sitting at 0.1 volts. So multiplying that by the root of 2, we will get 140 millivolts as a maximum and minus 140 milli as a minimum. Go through this whole exercise exactly the same and find that the minimum is just the negative of the maximum. Right, so if you increase the current in this current source, you increase the overdrive voltage and you increase the input differential voltage. So if you have very large inputs, you need to run this with a bigger current. Right, looking at our amplifier and its parameters from here on, we probably need to do the small signal model. So all DC sources get switched off and becomes grounds, and a current source becomes an open circuit like this. And due to our differential nature, this point between the two amplifiers when they're in balance is 0 volts. Right, so if we look at this, cut the circuit in two right here, we have two common two common source amplifiers, and that will actually help us greatly in our analysis. Okay, before we go to the rest of the analysis, if we look into this side of the circuit, our input impedance is infinite. If we look into this side, our input impedance is infinite. So that means when we are looking in both inputs at the same time, we have double infinite. So our differential input impedance is infinite by definition for our MOS amplifiers. If we were to go and place a resistor right here as a load and we view both ways from our load or our output into our from our load into our outputs, we will see two drain resistors and these output impedances right here are these transistors as well. But if it's a perfect transistor, we will just be seeing 2 times the drain resistors at our output. Also, if we are using just one output and we are looking into the amplifier, we are just seeing 1 time the drain resistance. So for fully differential mode, the output impedance is 2 times RD, and for single ended, it is just RD for our output impedance. Right. So if we were to split this circuit, we will see two common source amplifiers using the bias current divided by 2 gives us our drain current, and with our transistor specifics, our transconductance will be 10 milliamperes per volt. Right, so on the one side we will insert our input differential voltage divided by 2, and on the other side we will insert negative our input differential divided by 2. So V out 1, if we see this as a common source amplifier, will be the transconductance multiplied by the drain resistance multiplied by the input. That will be our output 1, V out 1 right here. Equivalently for V out 2, so here is just the negative, so we have minus GMRD, and this side we will have plus GMRD. So if we insert a load here in between and take the differential across that resistor, we will find V out 2 minus V out 1 is GMRD times VID. Right, so that is our differential gain. So the output differential divided by the input differential is GMRD. So 10 milliamps per volt times 10 kilo ohms will give us 100 volts per volt differential gain for this amplifier. If we do not neglect the output impedance of a transistor, our equation will just change to have RD in parallel with R out. Right. This also brings us to the single-ended modes. If we just take the one output right here, our gain will be half. Okay, since we are only using one half of a circuit and one output, the gain will be half of the fully differential mode. So if you need to calculate the gain for a single-ended converted circuit, it is half times GMRD. This brings us to our common mode signal, or our common mode for our amplifier. Now, if we drive the inputs equivalently and our current source goes to infinite and we have a resistor in parallel with our current source, RSS will be sitting down here between the two amplifiers. Okay, so this point right here is not at 0 volts anymore with the common mode signal or the common mode input. It's not applicable. Right, so we can split this signal in two like we did with the differential amplifier or the differential small signal, and we can do that by multiplying the RSS value by 2. So 2 times RSS in parallel with 2 times RSS is RSS. Now if we look at this amplifier right here, we are having a common source amplifier with degeneration resistance. And that means that we have a decrease in gain. Right. So V out 1 is again equal to V out 2, and that would be minus GMRD over 1 plus 2 times GMRSS. That is a typical equation we had with degeneration. Now, this 2 times GMRSS is most of the time much greater than 1 for these differential amplifiers, especially since this is in the kilo ohm range and the transconductance is purely millis. The answer will always be much greater than 1. Okay, so if this is much greater than 1, the 1 can disappear from here, the transconductances will cancel, and we will find that V out 1 is equal to V out 2 is our drain resistance divided by our source resistance, or 2 times our source resistance, and that is the amplification for a common mode signal. Right, so if we look at these individually, we will see that the common mode signal is multiplied by RD over 2 times RSS. Ideally, when we're doing fully differential, we will subtract V out 2 and V out 1, and if these things are exactly the same, the output will be equal to 0. So in perfect circumstances, the common mode gain for a differential amplifier or a fully differential amplifier will be equal to 0. Okay, this means the only thing that can affect your common mode gain is defects or differences in your drain resistors or differences in your transconductances for these amplifiers. So if you introduce a change in the drain resistor or a change in the transconductance, these equations will boil down to, for a difference in resistors, to delta RD over 2 RSS, and for transconductance, the delta of the transconductance but divided by the transconductance. So this is the percentage difference in essence multiplied by the ratio of these resistors. Right. So since it's easy to introduce a difference in drain resistors in simulation, the others is possible. It's just more difficult to show. If we let the two resistors differ by 200 ohms, the common mode gain will be 1 millivolt per volt for a RSS of 100 kilo ohms, and for 8.2 kilo ohms it's 12.2 millivolts. So I will show you this in the simulations. So if we take a look at the common mode gain for just a single-ended, whether you're taking V out 1 or V out 2, you are only looking at one output at a time. So it doesn't matter which one you're taking, the output, the common mode gain will be RD over 2 times RSS and inverted. So looking at the common mode for single-ended, it will be 50 millivolts per volt for 100 kilo ohm, and for the 8.2 kilo ohm it will be 0.61 volts per volt. So the larger your current source impedance, the better your common mode gain would be. So that is why biasing with a resistor is very bad for using single-ended applications. So you will find that this is most of the times current source is being used and not resistors. Though it is possible with resistors, just be aware that you will have very large common mode um, signals. Okay, so the attenuation is not as great. This brings us to our last topic, and that is output offset voltages. Now, for our amplifier, since the drain voltages are the same with matched transistors and matched drain resistors, the two DC voltages will always cancel out. They will be subtracted from one another. But there will be output offset if there is mismatches in these components. So again, with a mismatch in our drain resistors, we will see an offset voltage on the output of our amplifier, and this is the overdrive voltage divided by 2 times the percentage difference in our components. And this offset voltage needs to be multiplied by our differential gain to actually get the output offset voltage. Right, so this one is easy to simulate. With our gain of 100 that we calculated earlier, this will be 100 millivolts of offset. And this is only for differential mode. For single-ended, your output offset will be the drain voltage plus whatever this small amount of voltage is. So typically for the single-ended conversion, you need to take the output through a capacitor, which removes these offset voltages in any case, unless you're using that voltage to bias a next amplification stage. Okay, so in our differential, if we have a difference in our drain resistors, we will see 100 millivolt offset. The widths and lengths, if there is a difference in the widths and lengths of our transistors, it will cause offset. And if there is a difference in threshold voltages, it will also cause offset. So to combine all three of these, you take the squares of each one, sum them, and take the root, and that will give you your offset. And remember, for the output offset, you need to multiply with your differential gain. Okay, simulating these two effects is easy, but it's easier to show it with a difference in our drain resistors. So in summary, before we go to our simulations for a fully differential output, we will have GMRD as our gain, and we can have full swing across VDD and VSS. Our common mode is only influenced by differences in transconductance and drain resistors. Our output impedance is 2 times RD. Our input impedance is infinite. And remember that common mode rejection ratio is the absolute of our differential gain divided by our common mode gain, and then 20 log of that. For our single-ended differential amplifier, you can get rid of one of the drain resistors, and then the output on this side, if you look at this amplifier, just this half, this is a common source amplifier. So this is your inverting terminal, and this side will be your non-inverting terminal. So single-ended differential amplifiers will typically be in this form without the drain resistor. You can also see this as a common drain input going into a common gate amplifier from this side, and that is a typical configuration if you actually ground the inverting terminal. So this is one of the amplifiers that we discussed in multi-stage amplifiers. But in any case, half the gain, half the output impedance, input impedance is still infinite, but we will always have common mode gain, which is the ratio of RD over 2 times RSS inverted. Right, so let's go and have a look at our simulations and see how it correlates with everything that we calculated during this analysis. Our first simulation here is our DC analysis. So if we run this, obviously 1 milliampere in the current source, 500 micro balanced on both sides, and almost minus 1.6 volts here at VSS. So this is our VGS voltages right here. And if we measure here, this is at 5 volts and that is at 5 volts. So those are the drain voltages that we had in our analysis. Okay, so that is the DC. The current is split perfectly. Let's go over to our common mode simulation. For our common mode simulation, I introduced a RSS value down here. So resistance for our current source. I'm placing in a 1 volt signal on both inputs. I also introduced a difference between the two resistors of 100 ohm and a very large load resistor of 22 mega ohms, just so that we take it over a very large output. So if we run this and we measure this side, we see a signal running on some sort of offset right here, and on this side another signal running on some sort of offset. Okay, so if this is our Vout2, we need to subtract it to get our output voltage across our resistor like that, and here we go. So if we view this, we can see that we have a 100 millivolt offset roughly where this signal is sitting on. And if we take our cursor and we measure the peaks of these two signals, this is sitting at roughly 2 millivolts. So 2 millivolts divided by 2 volts is 1 millivolt per volt. So that is our common mode gain. Right, so 2 milli peak to peak out, 2 volts peak to peak in. Common mode gain, you can also do this using the AC analysis right here. So if you run our AC analysis, you will get our common mode gain at minus 60 decibels. So that is 0.001, which is 1 millivolt per volt. Right, so this is with a 1% mismatch. If we were to make this 10 kilo ohms and 10 kilo ohms, see that this has dropped to something very, very low. There is almost no signal running in here. If you look at the transient like that, there is a straight line. There is no signal sitting across here, although that is the input. There is also no DC offset on this signal right here. Alright, so that is the common mode of our fully differential amplifier. And if we run this again, put it back to transient, sorry. If we run this again with a differential or with mismatches, we will see our offset right here, right? Now let's decrease this to say 10k across this. And suddenly our output common mode increases. It's now 20 millivolts per volts roughly. Okay, so the resistance down here for your current source plays a big role in your common mode gain. So for ideal current sources where this impedance is infinite, there will be perfect common mode rejection. Next up are differential modes. I just put this across one half of a circuit. It doesn't matter if I split this in two or just use it like this. If we run our simulation, matched resistors, see that this is from 9 volts down to 0, and this one is inverted from the other signal. So both sides are inverted, and if we were to go and take our non-inverting output and we subtract our inverting output, which is at node 1, we almost have from positive 10 volts down to minus 10 volts as the output of this amplifier. So that is almost rail to rail output. Right, so 100 millivolts in, almost 10 volts out. The gain of this should be at 100 for differential mode due to the output impedances of our transistors that will typically be a little bit less. But if we do our simulation, right here we have 40 decibels of gain through our amplifier. So this is 100 volts per volts gain. Right, so that is the differential mode for current sources. The next simulations will be with purely resistive biasing. Right, so in this one I have placed mismatched resistors, a single ended output through a capacitor, and then just our RSS right here. So if we take a single ended output right here, we have 600 millivolts with a 1 volt input. So that gives us that 0.6 volts per volts common mode gain for the single ended when using a resistor. Node 2, node 1, note the offset. If we subtract these two, we get an offset of 100 millivolts as predicted before, and now our common mode output here for a 1 volt signal is 24 millivolts. Divide by 2 is about 12. If I remember correctly, this was about 12 millivolts per volt common mode gain that we calculated beforehand. Okay, so with a difference of 200 ohms. So using a resistor down here, that can give you your bias, but it will influence your common mode gain very drastically. Okay, let's have a look at the differential mode with a resistor. Right, our differential mode, if we run this, note that everything is exactly the same as it was. So when you're doing fully differential using a resistor bias is not a problem. There is our output. Our gain dropped a little bit, but I think that is due to this not being a current source anymore, but the E12 resistor. So yeah, we can still get fully differential using a resistor like this. Then I still have to prove two things. And that the first is if we have 20 kilo ohms here, is that our gain will be half. So this will go down to around the 4 volt mark. Okay, so that is 20 kilo ohms output, and no matter what input size we provide here, let's go with 1 meg, it won't make any difference on our output. Okay, so our input impedance is infinite and our output is 2 times our drain resistance. Great, on to our single-ended conversion. Right, our single-ended conversion, see that I left out this one drain resistor on this side, input is here, and our output will be in the same phase. So if this is 100 milli, that is in the same phase but 4.5. Note that we can't reach the rail voltages with our single-ended conversion. This is pretty much as high as it can go. The differential makes it possible to go to our rails. Okay, so there you go. Any case, so single-ended, half the gain. So 100 milli in, 4.5 volts out, that is about 45, and we calculated it to be at about 50 volts per volt. So half a gain and half the output impedance like this. So if we insert 10k here, it will half again. Okay, so if you can do fully differential, the single-ended is mostly just half of everything that you had, but the common mode, there is a big difference for the common mode rejection ratio between the two configurations. And that is it for MOSFET differential amplifiers. Thank you for watching and see you in the next video.